Now we should see the working of full wave rectifier using bridge circuit. Let us construct the bridge circuit using 4 diodes. Let me construct a bridge. So this is 4 diodes connected. There are 5 diodes coming. So let me delete one of the diode. So I have deleted one. So let me have a voltage source that will generate the sine wave, which is the AC signal. Let me place it here. Let me set the parameters of this AC signal as 0 volt DC, 10 volt DC DC amplitude. Let us assume the frequency as 50 Hertz. If there not be any delay, these parameters let us have n cycles, and let us have a resistor over here. Let me change the value of the resistor to 1 kilo ohm. Done. Now let me do the connections. Now the connections are made. So I have labeled the lines also. So this is the output line OP. So this is the output node. So I have connected a load resistor of 1 kilo ohm. So you can see I'm also having two input nodes, that is IN plus and IN minus. So this is exclusively written as IN plus IN minus because the input voltage is measured with respect to minus, whereas the output is measured with respect to ground. So the input voltage is a sine wave of 10 volt peak with 50 Hz frequency. So of course the transient response is selected because I want to see the output waveform in terms of respect to time. The final time is taken as 20 millisecond, the stop time, so which enables me to see at least 2 cycles. So let me run the program. So I want to see the input voltage. For input voltage, since it is differential voltage, so let me measure the input voltage at IN plus with respect to IN minus. Not to do this, you hold the probe at input plus and input minus. So we just do it this way. Now you have input plus input minus, and we have the output voltage here. So there is some problem. I'm not getting the voltage. So let us see what is the problem is. Now you can see there is the output was expected to be a ripple or a fully rectified signal. I'm getting a 0 volt. Even the input is also not proper. So let me see what is happening here. So if you carefully observe the circuit diagram, see there is a dot which is being unnecessarily created here. So actually the input voltage negative would have been connected to this point. Now while running this track, okay, let me just redo this. So let me disconnect this wire, and let me disconnect this wire also. So you have to be a bit careful when you're running any line. So ensure that it is not crossing the edge of the transistor connection or any component connection. Now you can see there is no node created. See here, there is no dot here. So since there is no dot here, now there is no connection. So let me run now and try to see whether the output is okay or not. Are we getting out? Now we can see everything is fine. But still we are not getting a proper input waveform. It's purely because it is V in minus. So I had to properly have this input voltage connected. Let me just take out this input. So over here, let me measure the input voltage from IN plus to IN minus. I'm just measuring it now. Now we can see everything is fine. Now to make the waveform bit, so let me have this mark data points. Now you can see now it's more clear. In order to make it much more clear, what I can do is, and again go back to this dot trend, and you can make this even smaller. So let me make this another few more points. Let me make it 0.00. So this will make the waveform much more. You can see it is having more number of points to plot the graph. Now it is more clarity in the waveform. Now this is the output waveform. If you actually see the difference between this input and output, so it will be equal to VDM. So that you can make the measurement, because in each of the half cycle only one diode is connected. So let us continue this half wave rectification by putting a filter. So let's stop it here. So let me do it using the full wave rectification with filter. Now the circuit is modified by connecting a capacitor of 100 microfarad across the load resistor. So let me now run the circuit. So upon running this circuit, we are having the input voltage is the green one, where you can see it is at V in plus and V in minus difference. You can clearly see the output voltage is now the ripple voltage. Now we can actually find the ripple voltage. You can have two cursors on the output. You can place one at the top, so one at the maximum, which happens to Vp minus Vd1, and this is the minimum voltage. So I can further zoom this. Now you can see you can slightly adjust it to the profit value. Now the difference of those two is 674 millivolts. So that's what is ripple voltage. You can certainly verify this using the calculate from the theoretical equation, where you have the ripple voltage for full wave rectifier with which happens to be Vp minus 2Vd1 by 2Frs. So this way you can get a rectified waveform. So let us see the regulated circuit. We connect a regulator to this circuit and then redo the simulation. So in order to get the regulator, so go to this components. Here we have so many libraries in which there are power products. Just go on clicking to each one of them, look for a regulator, which is here you can see there is a 1.5 ampere, so on. So you can either select this, or you can select any regulator which is a constant output voltage. Let me select this and then place it here comfortably. So now I'm just placing it now here. So let me do the connection of this. By mistake I have connected a regulator which is adjustable one. So let me go back and select a regulator which has got a fixed voltage. Now you can see it is even though it is given as fixed, I don't know why it is, or you have an adjusting over here. So let me just again look for something. Now here it's adjustable. Now this is adjustable. Now this is also adjustable. So let me look for. So this is fixed voltage, but still there is an adjustable here. So let me just see. Okay, upon simulating what happens. So let me just simulate this now. So as per the description of this regulator, it says that a fixed 12 volt, but I don't know why this ADJ is given. So let me run this program. So make sure that since the output voltage has to be 12 volt fixed, the input should be far greater than 10. So let me make this input voltage something like 20 volts and then simulate this. Now let me run this. Now we should look at this output voltage. Even though I just named this as output, this output happens to be the input for your regulator. The final output is here. So let me stop the simulation and then do that correction, label it properly, and then come back to the output simulation. Okay, now you can see we have modified the labels. So I have just modified this label as regulator input, because this is the input that is given to the regulator and this is the regulator output. Let me run this program and then see what is the regulator input. And so this is the regulator input, which is varying. Let me just see what is regulator output. As you can see now, so regulatory input voltage is the capacitor voltage which is having a ripple, whereas the regulator output is constant at 12 volts. You can clearly measure. This is the cursor 1, cursor 2 are both are on the output line. Now you have this as 12 volt, meaning the output voltage is 12. You can also measure the input voltage. The input voltage is 17.87, whereas the output is 12 volts, meaning that we are having a regulated voltage. This says when the input voltage is more than the minimum voltage, we can actually find what is the minimum voltage required to get a proper regulation. For that, I can just move this cursor over here. So whenever this becomes constant, maybe over here, let me just zoom this portion. So from this, we can clearly make out this is at this point. At this point, now your output voltage is constant here. What is the corresponding input voltage? The corresponding input voltage is 13.03. So if the input is more than 13, we will get an output voltage of 12 volts. Now I can see the corresponding output voltage is 12 and the input is 13.7. So that is 11.95. The input voltage is anything more than 13 point something, the output voltage is constant at 12. Meaning the minimum input voltage should be there at the input of your regulator for this IC is 13 volts. Suppose if the input voltage is less than 13 volts, so let us see what happens to the output voltage. So let us intentionally reduce the input voltage from 22. Let us make it around 15 volts. Let us try to see what happens if I run this program. I'm just running the program. Let us see what happens. Suppose if the input voltage to the regulator is less than 13 volts, output voltage will not remain at 12, so it will come down. So we will just carefully look at, does your input voltage to the regulator goes less than 13 volts. If it is going less than 13 volts, it is the output voltage is bound to reduce below 12. So you can see here it's already happening. So the input voltage is going less than 13. See that output voltage is not constant. Here it is constant. The output voltage is constant here. When it comes to this point, the output voltage is not constant. So you can carefully see here. So this whatever variation in the input voltage is now, you can see it is now when it is 13, you are having it as well. Let me just put this output also. You can see output is 12, output is 11.97, the input is 12.91. Suppose if your input voltage reduces, input voltage is now 12.7, you can see corresponding output voltage. Corresponding output voltage has also reduced to 11.8. Now it is not doing the regulation. Now the output voltage is no more constant because the input voltage is less than the minimum required voltage for this IC, which is 13 volts. So we have to be very careful that the input to the regulator should be minimum voltage. So which we will specify in the data sheet. For this particular IC, it is 13 volts.